Welcome to the delicious world of food and culinary science, where math meets your kitchen. Today we'll explore the fascinating equations that govern cooking, baking, and food science with entertaining examples. Let's start with the most fundamental equation in cooking: heat transfer. This is the heat equation. Q is heat energy, M is mass, C is specific heat capacity, and delta T is temperature change. But what does this actually mean when you're cooking? It tells you exactly how much energy you need to heat your food to the right temperature. Imagine a pot on a stove. The flames transfer heat energy to the water molecules, increasing their kinetic energy and temperature. Let's use a real example: boiling water for pasta. We have 2 kilograms of water, which is about 2 liters. The specific heat capacity of water is 4,184 joules per kilogram per degree Celsius. We want to heat it from room temperature, 20 degrees, to boiling at 100 degrees, so delta T is 80 degrees. Plugging in our values, we get 800 joules of energy needed. That's about 670 kilojoules, or roughly 160 food calories worth of energy just to boil water. Funny enough, boiling water for tea requires about the same energy as the calories in one chocolate chip cookie. Next, let's explore diffusion, which explains why marinades work. This is Fick's first law of diffusion. J is the diffusion flux, D is the diffusion coefficient, and dC over dx is the concentration gradient. In simple terms, flavor molecules move from areas of high concentration to low concentration. Picture marinating chicken. The flavor molecules from your marinade slowly diffuse into the meat, creating delicious flavor throughout. So here's a practical question: how long should you actually marinate chicken? The time needed is proportional to the thickness squared divided by the diffusion coefficient. For chicken that's 1 centimeter thick, about 2 to 4 hours gives optimal flavor penetration. If your meat is twice as thick, you need 4 times as long because of that thickness squared relationship. Think of it like perfume spreading through a room, except much slower because meat is denser than air. Now let's talk about enzyme kinetics and meat tenderization. This is the Michaelis-Menten equation. V is reaction velocity, V max is maximum velocity, S is substrate concentration, and Km is the Michaelis constant. Enzymes in fruits like pineapple and papaya break down the tough collagen proteins in meat. The enzymes act like tiny molecular scissors, cutting the long protein chains into smaller, more tender pieces. But be careful. Leave it too long, and those enzymes will turn your expensive steak into complete mush. For most meats, 30 minutes to 2 hours is the sweet spot for tenderization without mushification. Pro tip: temperature matters too. Enzyme activity roughly doubles for every 10 degrees Celsius increase in temperature. Let's move to bread making and the ideal gas law. The ideal gas law: P is pressure, V is volume, N is moles of gas, R is the gas constant, and T is temperature. When yeast ferments sugars in dough, it produces carbon dioxide gas, which makes bread rise and become fluffy. The carbon dioxide forms tiny bubbles throughout the dough, creating that wonderful light and airy texture we love in bread. Here's an interesting question: why does bread dough rise faster when it's warm? The answer is twofold. Higher temperature directly increases gas volume according to the ideal gas law, and it also speeds up yeast metabolism. At constant pressure, the volume ratio equals the temperature ratio in absolute temperature. Going from 25 to 35 degrees Celsius, that's 298 to 308 Kelvin, gives only about 3% volume increase from gas expansion alone, but the yeast activity roughly doubles in that temperature range. That's where the real rising magic happens. Think of it like a balloon left in a hot car versus a cold garage. The hot one expands, but imagine if it also had a creature inside blowing more air. Now for everyone's favorite: the Maillard reaction that creates delicious browning. This is the Arrhenius equation for reaction rates. K is the rate constant, A is the pre-exponential factor, EA is activation energy, R is gas constant, and T is temperature. The Maillard reaction creates that beautiful brown color and incredible flavor in everything from seared steak to toasted bread. Raw, pale food transforms into gorgeously brown deliciousness through this chemical reaction between amino acids and reducing sugars. The Maillard reaction really kicks in around 140 to 165 degrees Celsius. Below that, not much happens. Pop quiz. Does searing meat actually lock in juices like everyone says? Surprise! It doesn't lock in juices at all. That's a myth, but it does create incredible flavor through the Maillard reaction. The reaction rate approximately doubles for every 10-degree increase in temperature, which is why high heat creates better browning. Think of it like toasting bread, but instead of just bread becoming crispy, you're creating hundreds of new flavor compounds. Let's discuss pH and why it matters for food preservation. pH is defined as negative log of hydrogen ion concentration. It measures acidity on a scale from 0 to 14. The pH scale ranges from 0 for very acidic through 7 for neutral to 14 for very basic or alkaline. Most dangerous bacteria struggle to grow below pH 4.6, which is why acidic foods last longer. This is the secret behind pickles, vinegar-based sauces, and fermented foods. The acid keeps the bad bacteria away. For reference, lemon juice has a pH around 2, while milk is about 6.5, close to neutral. Here's a practical question. Why do recipes always tell you to add lemon juice to guacamole? 2 reasons. The acidity slows down the enzymatic browning that turns avocados brown, and it helps prevent bacterial growth. Fun fact, because pH is logarithmic, going from pH 2 to pH 4 means 100 times less acidic. Math makes food interesting. Now let's explore emulsification, the science behind mayonnaise and salad dressings. Everyone knows oil and water don't mix. They separate into layers because of their different molecular properties. But with an emulsifier like egg yolk, we can trap tiny oil droplets in water, creating a stable emulsion. Emulsifiers are special molecules with both water-loving and oil-loving parts, acting like molecular diplomats. Surface tension gamma equals force over length. Emulsifiers reduce this tension between oil and water. Mayonnaise is actually 70 to 80% oil by weight, but it looks and acts like thick cream because of emulsification. Quick question. Why do fancy salad dressing recipes often include a tiny bit of mustard? Answer. Mustard contains natural emulsifiers that help stabilize the oil and vinegar mixture, keeping it from separating. Think of emulsifiers like a host at a party forcing 2 people who hate each other to hold hands. Awkward, but effective. Let's discuss osmosis and why brining makes meat juicier. This is the osmotic pressure equation. Pi is osmotic pressure, I is the Van't Hoff factor, M is molarity, R is gas constant, and T is temperature. When you brine meat in salt water, water molecules move from low salt concentration to high concentration areas through osmosis. The salt solution penetrates the meat, bringing water with it and seasoning throughout, not just the surface. A typical brine is about 5 to 8% salt by weight, roughly the same saltiness as seawater. A good rule of thumb is to brine for about 1 hour per pound of meat, though this varies with thickness. The payoff is huge. Brined meat can retain up to 10% more moisture after cooking, staying juicier and more flavorful. Important question. Can you over-brine your meat? Absolutely yes. Too long in brine makes meat unpleasantly salty and can actually break down the texture into mushiness. The sweet spot is 8 to 24 hours for chicken and 12 to 48 hours for a whole turkey, depending on size. Now for the sweet science. Caramelization of sugar. When you heat sucrose, it breaks down into hundreds of complex flavor compounds through thermal decomposition. Table sugar melts around 160 degrees Celsius and begins browning and caramelizing around 170 degrees. White sugar transforms through melting to golden liquid, and finally to rich brown caramel with incredible flavor complexity. Caramelization creates over 100 different flavor compounds, from buttery to nutty to slightly bitter notes. Unlike the Maillard reaction, which needs proteins, caramelization is purely about sugar breaking down from heat. Interesting question. Why does sugar taste amazing when caramelized but terrible when burnt? Past about 180 degrees Celsius, the reaction creates more bitter and acrid compounds that overpower the pleasant caramel flavors. Pro tip: adding a little water to your sugar helps control temperature and gives you more time before burning occurs. Think of it like tanning at the beach. Stay just long enough for a golden glow. Too long and you're painfully burnt. Finally, let's understand thermal conductivity and why different foods cook at different rates. This is Fourier's law of heat conduction. Q is heat flux, K is thermal conductivity, and nabla T is the temperature gradient. Different foods and materials conduct heat at wildly different rates, which affects cooking time dramatically. Here we see heat conducting through different materials at different rates. Metal is fastest, then water, then meat is slowest. Let's look at some actual thermal conductivity values. Aluminum has a thermal conductivity around 200 watts per meter Kelvin. Water is about 0.6 watts per meter Kelvin, and meat is roughly 0.5 watts per meter Kelvin, similar to water since meat is mostly water. This huge difference is why your metal pan heats almost instantly, but a thick steak takes many minutes to cook through. Final question. Why do chefs always tell you to rest meat after cooking? During resting, heat continues, conducting from the hot exterior toward the cooler center, evening out the temperature. Rest steaks for 5 to 10 minutes, and large roasts for 20 to 30 minutes for optimal temperature distribution. Think of it like letting a hot pizza cool slightly. The cheese that was volcanic slowly becomes safe to eat as heat spreads. Let's wrap up with the key takeaways from our culinary science journey. First, heat transfer equations tell you exactly how much energy you need to cook food to the right temperature. Second, diffusion explains why marinades work and how long they need to penetrate meat. Third, enzyme kinetics shows us how to tenderize meat without turning it to mush. Fourth, the ideal gas law explains why bread rises and how temperature affects the process. Fifth, the Maillard reaction and caramelization create those incredible brown flavors we love. Sixth, pH is crucial for food safety, preservation, and controlling enzymatic reactions. Seventh, emulsification allows us to create stable mixtures of ingredients that normally hate each other. Eighth, osmosis explains why brining makes meat juicier and more flavorful throughout. Ninth, thermal conductivity differences explain why different foods and materials heat at such different rates. And finally, understanding the science behind cooking makes you not just a better cook, but helps you troubleshoot problems and create new dishes. All these equations work together to explain the magic happening in your kitchen every single day. Always remember, cooking is just chemistry you can eat, and now you understand the equations behind the deliciousness. Next time you're in the kitchen, you'll recognize these scientific principles in action all around you. Happy cooking, and may the equations be ever in your flavor. Thanks for joining this tasty journey through food science.